All right, this is 11.1, first lesson in our statistics unit, and this lesson is going to be about normal distributions. I need to remind you about a couple of things from earlier classes that will kind of draw on this unit. The first thing is what a dot plot looks like and means. So these are a couple of examples of dot plots. This one at the bottom I like. It represents some classes at a school, and each of those dots represents one class. So altogether, this is showing you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is showing you information about 16 different classes. So what that dot plot means is that there were 4 classes that had 28 students. There were 3 classes that had 30 students. So the smallest class at this particular school had 25 students. The largest class had 30 students, and the most common number of students was 29. So these are dot plots, and hopefully they make sense to you. The next thing I wanted to remind you about is frequency distributions. In some ways they're very similar to dot plots, but instead of having individual dots to represent each data point, we have these bars, and instead of having just one single value along the bottom, we have what we call classes of data. So this whole bar right here represents all of the people who were between ages 18 and 21, and it looks like if I had to estimate, I'd say that there were 7 people in that age group. Oh yeah, and sorry, we have a table over here that shows that. So a frequency distribution is a lot like a dot plot, except for with classes. Similarly, we could have a probability distribution. So these two graphs are identical except for what is listed on the y-axis. So this one is just like the one we just looked at where it lists the number on the y-axis. So this is saying in the age group 30 to 39, there were 80 or really close to 80 people. And the second one, instead of listing the number of people, it lists the percentage. So for that same age group, 30 to 39, that would be probably something like 17% of the total group. And then in age group 50 to 59, that looks like it's right around 25% of the whole group. Now, one of the advantages of a probability distribution instead of a frequency distribution is that if we've displayed all of the data, we know that the total of all of those bars, if we added them up, would be 100%. Whereas this one, if we added them all up, it would be whatever the total number of people. So sometimes that's nice to know the total number of people, but sometimes it's advantageous to just be able to calculate the percent and know that the total percent is going to be 100%. Okay, another thing to remind you of from prior years, in 9th grade, you should have calculated a standard deviation, and this year in Math 3, we aren't going to be calculating standard deviations, but we are going to be using standard deviations. So I wanted to remind you what a standard deviation means. After the test last time, I had you practice calculating a mean and a median for some sets of data. The mean and the median are both measures, we call them as measures of center of the data. They tell you where the center of the data is. Standard deviations go with those, but instead of telling you about the center, they tell you about how spread out the data is. So I have 2 box plots up at the top. This one has a really small standard deviation. It's not very spread out. This one has a large standard deviation. It's very spread out. two more box plots down here. You can see both of these oh my goodness, dot plots have a median of 70. But the set above is much more spread out than the set below. So we would expect this top set to have a much larger standard deviation, and this set below a much smaller standard deviation if we were able to compare them. Just like dot plots, when we look at a frequency distribution, we can also sort of see how big or small the standard deviation is, or maybe not exactly, but definitely to compare. So this distribution on top is, between -3 and 4. It would have a much smaller standard deviation than this set that's spread out between -6 and 6. So standard deviation is just a measure of spread. And when you have information about a set of data, you kind of need both things. You need a measure of center, like the mean or the median, and you need to know something about how spread out it is, like the standard deviation. Okay, so now we're getting into the scope of what we need to do today in Math 3, which is to learn about normal distributions. So this is a famous data set collected back in the 1800s. The data was collected from some men in the Scottish militia. So they collected data on their chest size, how burly these military guys were. So when you look at the distribution over here, it says a couple of symbols that you need to be aware of. This symbol right here is a symbol that we use for the mean. So this data set has a mean right here of 40. And the other symbol that you see there right here, that symbol sigma is for standard deviation. So this particular set had a standard deviation of 2 inches. So when you look at this data set, you might notice that it has a shape somewhat like a bell. And we call this a bell curve sometimes, and it also is sometimes called a normal distribution. And that's what we'll be talking about today, is data sets that are distributed somewhat like this data set. They have a few characteristics that they all have in common. They all have this bell shape. The mean is always located right at the center. It's also the mode and the median of the data. And it's very symmetric. Both sides are approximately equal to each other. This was a set of 5,338 men. If we were able to collect more and more data, making those bars smaller and smaller or less wide and less wide, it would actually create this nice smooth curve. And so this is sort of a theoretically perfect normal distribution. What's interesting about the normal distribution, I guess, is that when you think about this number line along the bottom, when we're setting up a normal distribution, we always start by putting the mean right in the middle. So I have the symbol there for mean. And instead of counting out by ones or counting out by fives or tens or whatever your scale might be, the thing that we want to count out by is standard deviations. So this notation is a little bit tricky at first, but I'm sure you'll get to understand it. So this is saying that the mean is in the center, and this next one to the right of that is saying it's 1 standard deviation above the mean. And this one next to it would be 2 standard deviations above the mean, and this one next to it would be 3 standard deviations above the mean. And in the other direction, it would be 1 standard deviation below the mean. 2 standard deviations below the mean and 3 standard deviations below the mean. So for example, with our Scottish guy, the mean is 40, that would be right in the center, and for that set, the standard deviation was 2. So this would be 2 above the mean, this would be, so 42, the next one would be 2 more, so 44, and 46. The standard deviation essentially tells you what to count by. So for our men, this side would be 38, 36, and 34. So when you have your distribution broken up into sections by standard deviations like this, a normal distribution has always the same percentages in each section. These two sections closest to center are each accounting for 34% of the data. In the next increment here, we have 13.5% of the data. In the next section, 2.35%, and in the very last outer section, 0.15%. And it's symmetric, so it's the same on both sides. Now, the Scottish men, their distribution was approximately normal, but lots of other naturally occurring data sets have this sort of distribution. For example, if you collected data on the heights of men in America, it would be normally distributed. The mean is about 5'10", and the standard deviation is about 3 inches. If you collected data on the length of fish in a lake, it's most likely going to be normally distributed. Lots of naturally occurring data sets are normally distributed. So we're going to try to apply these percentages in a few problems now. Here in your notes you have these percentages written out for you to use. Probably at first you're going to need to refer to those, and then after a while you'll get those percentages memorized. Okay, so this one says the normal distribution has a mean of mu and a standard deviation of sigma. An x value is randomly selected from the distribution. Find each of these probabilities. I think this notation is a little bit challenging. So this is probably one of the more difficult things that we'll do during this lesson. So the mean is mu. With the normal distribution, that mean is right in the middle. The standard deviation is sigma, so that means we're counting out by sigmas. I'm not going to write the mu, I'm going to just write the sigmas. This would be the mu plus 1 sigma, 1 standard deviation. This would be plus 2 standard deviations, and this will be plus 3 standard deviations. And on the other side, we'll just count back by standard deviations. Okay, now I'll put the mu's. Okay, so the first question says, what is the probability? The P stands for probability of x being greater than the mean plus 1 standard deviation. This is one quantity. We want to know what's the probability that x is greater than that value. So on our distribution here, that value, the mean plus 1 standard deviation, is right here. And we are wondering about what percent of the data is greater than that. And this portion of the normal distribution is the portion where the values are greater than that value. So to answer the question of what is the probability of that, we're just going to add up those percentages in the shaded in sections. For this unit, when we ask for probabilities, we'll I think always be answering those questions with a percentage and not a fraction. So we add up those 3 sections. and we get 16%. Okay, let's see what the next one asks us. I'm just going to remove this shading. Okay, the next question says, what is the probability that our x value, here's our x value, is between two standard deviations less than the mean and the mean? You can think of these values as the fences if you want. We want to know it has to be smaller than the mean, and it has to be larger than two standard deviations below the mean. So if we shade in that section in between those two values, it's these two sections. So to get the answer, we'll just add up those two percentages. 34% plus 13.5%, which is 47.5%. So the probability of the x value being between those two values would be 47.5%. Okay, we've got another probability that is between two values. What is the probability that x is between one standard deviation below the mean and the mean? So let's modify this. We now want that fence to be one standard deviation below the mean. Let's see if I can get that off. So we're talking about this section only. Well, that section is exactly 34%. And it's just that one section, so we don't have to add anything. Okay, last one. This one says, what is the probability that x is greater than mu, greater than the mean? Well, the mean is dead center. So when it asks you what's the probability of x being greater than the mean, that would be all of this stuff. So you could add up all those numbers to get your answer, or you could remember that the mean is exactly the center of the data, and it divides the data evenly into two groups, and there is a 50% chance that x would be greater than the mean. These things all add up to 50%. It's symmetric exactly, and there would also be 50% on the other side. So this particular probability that x is greater than mu would be 50%. Okay, so this type where it has the probability notation with those greater than or less than symbols, these are probably the most difficult type of problems that you'll be doing with normal distribution. The ones in context I think are actually a little bit simpler. So we're going to set this one up first, and then we'll do one more after that. The scores for a state peace officer standard and training test is normally distributed with a mean of 55 and a standard deviation of 12. The test scores range from 0 to 100. We're going to answer some questions about percentages. First, we need to set up our normal curve here. It tells us that the mean is 55, so that goes right in the center, 55. And it tells us that the standard deviation is 12. That's telling us what we are going to count by in each direction. So one standard deviation above the mean would be 67. I got that simply by adding the standard deviation, which is 12. And to get the next division mark right here, I would just add another 12. So this would be 79. And the last one is going to be 91. Again, we're just counting by 12s. And in the other direction, it's less than the mean by the standard deviation. So we're counting back by 12s. So this one would be 43, and if we subtract another 12, that would be 31, and another 12 would be 19. So we just count by standard deviations. Okay, so now let's look at these questions, and I'm going to shade the curve to help us answer the question. So the first one says, about what percent of the people taking the test have scores between 43 and 67? So we are talking about this section here. And at first you may need to refer to your diagram to get these percentages, but you'll know them after a while. Each of these sections is 34%, so we would have a grand total of 68% when we add those two together. All right, second question. An agency in the state will only hire applicants with test scores of 67 or greater. What percent of the people have test scores that would make them eligible to be hired by this agency? So this time we're looking for the percentage of people who score greater than 67. Well, 67 was right here. So in this case, we are looking for the area of the curve that's over here, shaded in light blue. Well, if you remember those percentages, this first one 13.5, the next one 2.35, and the last one is 0.15. So we need to add those three sections together to get our answer. And when we do that, we get 16%. Now there's another way of looking at this one that sometimes people like a lot, and that is to think about it using a little bit of subtraction instead of addition. So we know that 50% of the data are on the right side of the mean, so we could have said, well, it's 50% of the data, except we're missing that first section of 34%. So using subtraction, you could also get that 16% as well. All right, the last question says, about what percentage of people have test scores less than 55? Well, 55 is the mean. So there are 50% of the scores would be less than that mean. All right, let's try this one now. And I think that, let me check. Yeah, this is our last example, and then we just have one last thing to talk about. So a study finds that the weights of infants at birth are normally distributed with a mean of 3,270 grams. The mean goes dead center on a normal distribution. 3,270 grams. The standard deviation is 600 grams, so we're counting by 600s. So if we add one standard deviation, we get 3870. If we add another standard deviation and another 600, we get 4470, and another 600 gives us 5070, and I will count back by 600. So this first one is going to be 2670, 2070, and 1470. Again, the standard deviation was 600, so we're counting in both directions by 600s. All right, so an infant is randomly chosen. What is the probability that the infant weighs 4,470 grams or less? Well, here is 4,470 grams. So the probability of an infant weighing less than that would be all of this area. Most infants. So let's figure out exactly what that percentage is. I think this one is actually a lot easier to think of as subtraction. You know, you could add up each of these sections, but we're only missing these two. So the whole curve shows 100% of the infants. We are just missing 2.35 and 0.15 on the end. So we could just subtract those from 100 and we get 97.5%. So when some certain percent of the data are less than a certain value, we'll say that that value is uh, that percentile. So you may have seen, test results from tests you've taken in the past that said you scored in the 85th percentile. That's not saying you got 85% of the questions on the test right. That's saying 85% of the people scored less than you. So, if a baby was born and it weighed 4,000, um, that should say 470 grams, that baby would be the 97.5 percentile for weight. So percentiles come up in your homework a little bit. So just remember that percentiles mean that that's the percent that is less than that value. Okay, the second question says, what's the probability that an infant weighs 3,870 or more? So here's 3,870. It would be all of these percents. So we just need to add 13.5, 2.35, and 0.15. And when we add those together, we get that 16% of the infants weigh more than 3,870 grams at birth. Okay, so we're essentially done now. Just wanted to quickly let you know that while there are many, many, many things that are normally distributed, not everything is. Here are 3 histograms. The first one definitely has a normal distribution. It has that bell shape, it's symmetric, the mean is right in the center, and so this first one is definitely sort of a normal distribution. But the other 2 are not. They're what we call skewed distributions. The middle one is a skewed left distribution, and then the one on the far right is skewed right. When you're deciding if it's skewed left or skewed right, you just think about where sort of the tail is. So this tail is on the left-hand side, so it's skewed left. It means that the mean is to the left of the median. And then this tail over here is pulling, those values over there pull the mean towards them. So the mean is to the right of the median in that case. So it's skewed to the right. So these percentages that we've been talking about today, they apply to things that are normally distributed. You would not want to apply any of these sort of percentages to skewed data. So let's just look at these 2 curves really quickly, determine whether each of them is normally distributed. That first one, I think you can see that it's fairly symmetric. It sort of has this bell shape. So we would say that this one is normal or pretty close to being normal in distribution. This second one, though, definitely has this tail over here. So this one we would say is skewed right. That first graph, by the way, is the height of women in the United States, ages 20 to 29. And while I am no longer in that age group, unfortunately, I was the same height when I was that age as I am now. And here I am, right here on the curve. Not very close to the center on that one. All right, so that's it for normal distributions. Thank you.